Right, welcome to our video for the physics exam, the physics mock, which is tomorrow. We're going to be doing this, putting up this video on YouTube, and there will be a link on the Facebook page. These are the topics we are going to be covering, so we're going to be looking at resistance, models of the atom, nuclear fission and fusion, collisions and energy. These may well be the topics that might come up in the mock exam tomorrow, so if we cover these all in the 30 minutes we got, we should be in a good position for that exam. We're going to be using the interactive board tonight, so hopefully you can see this better. We're trying to improve this. This is a work in progress, so we're making it better for you based on your comments. So if you do have any comments or feedback following this, then please do give us those, and we'll make it better as we go along. The intention is to do more of these if you find them useful, and go from there really. So the first thing we're looking at is resistance. Okay, this is a type of graph. It's called a VI graph or an IV graph. It actually shows two things. It shows V, which is volts, the unit. It shows potential difference. So this is potential difference along the bottom. And along the side here, I actually stands for the current. Okay, so we've got current and potential difference. On this we've got three lines. Those three lines show the resistance of an object. The three lines are at different gradients or different slopes if you prefer. Okay, we've got the green line, which is very steep gradient or very steep slope. We've got the red line in the middle and the blue line, which is shallower. Those are straight lines, each of them are straight lines. That's because whatever this component is, it must be at a constant temperature, hence the line is straight. If it is a resistor, we would have a symbol. So we could draw a circuit symbol, we could draw some circuits. So circuits usually have a power source, and they have wires go round. And they have some sort of component in the circuit along with it. If we were to have a resistor is just a rectangular box like that in the circuit. Now if we wanted to measure the current of this circuit, we would need what's called an ammeter. An ammeter, the symbol is like that, not with a line through it, and that should be an A in it. So that would be our ammeter. And then if we wanted to measure the potential difference, or the voltage as we may know it, of the resistor, we have to put a voltmeter in parallel to it. A series circuit, which is what this is, means there is one loop. The circuit has one loop. Whereas in parallel, it means there is another loop. It could be a second loop, but you could have a third or fourth loop and it would still be a parallel circuit. So we've got a series circuit with the resistor in it, and we've got a voltmeter over that in parallel to it. So we could measure the current on here, and we can measure the potential difference here through that resistor. Then if we were to plot a graph, we could get lines for it. And on this one there is three lines. Okay, they show three different resistors. So they're different resistors, they have different resistance. The blue line, which is down there, this resistor has quite a high resistance. Okay? Now, this is a bit against what you might normally think. Okay? This has a high resistance because the slope is low. So it's got a low slope, which means high resistance. It's a bit backwards, this. Whereas the green line, in fact, that has a low resistance. Hence the line is really steep. So the resistance of that one is low. So this has a low resistance. That's a great S there, not very good at writing on this board. Low resistance. Okay, so we've got really steep line for low, shallow line for high resistance. It's a bit backwards to what you might normally anticipate. So that type of graph shows us potential difference on the bottom, current along the side, and it shows different resistors with different levels of resistance, high resistance, middle, low. Okay, they're all straight lines, so as I said, that means they must be an object that stays at a constant temperature because the line is straight. Okay, so that's what we're looking at there. This is a circuit, this is how we would measure it. We'd have an ammeter in there and a voltmeter across our resistor in that circuit. Okay, so that's a really good little bit of information, and we can measure these graphs and use these different graphs to measure different resistance in different circuits, or different components, I should say, that go on that circuit. Okay, so that's resistance. Some of the symbols you might come across, so this just shows you some of those symbols. So this one we talked about, this is a fixed resistor. So this one does not change. Some of them could be preset resistors, which have a setting that's set them to. They don't come up so much at GCSE, that's fine, we can kind of ignore those preset ones. Variable resistors are ones that could come up at GCSE, they're ones you can change the resistance of. We have these two again, potentiometers, they're not so important, but thermistor, definitely, that's another GCSE common type of resistor. This one, the therm bit, means it's dependent on temperature. So as you change the temperature, the resistance of this object will change. And this is a light dependent resistor, LDR. So this one, as you change the amount of light it receives, the amount of resistance will also change. So these are different resistors we could be looking at, but this is just a standard resistor, this one. This is the normal resistor you might get. And as shown, it's in a circuit here, and to measure the voltage across it, we've got a voltmeter in parallel to it. So across it, it must be across the component. So that's kind of a little bit about resistance, and flying on to our next topic, which we've covered resistance on our little chart, so we'll tick that off. Talk a bit about models of the atom. Now, some of you may have covered this in class, but it may be a topic that we haven't yet covered with our teachers. You may be yet to cover this. So it could be an important one to know a bit about. Early on, they used to think that an atom was just a solid ball that couldn't be split up or couldn't be divided in any way. So it was just a solid lump there. There wasn't really much to it. It just couldn't be split up any more than it originally was. That's where the word actually came from. Atomos means not being able to divide it. Later on, a guy called J.J. Thomson found these things, these tiny little particles that had negative charges, and they decided they were electrons. He then said, because of that, this model of an atom must not be correct, and he refined it. He came up with this model. Some of you might recognise that model was called the plum pudding model. Okay, what that model was is that this was like a bit of pudding. So imagine a Christmas pudding, if you like, a round Christmas pudding. This was the actual bit of the pudding, and that bit of the pudding was a big ball of positive, that's a plus in it, charge. So it had a big ball of positive charge. And then within that, there was these little plums, or currents, or raisins, of negative charge, these electrons that were there. Okay, they were inside that big ball of positive charge. So the pudding bit was a positive charge, a lump of positive charge, and the electrons were dotted through it. Okay? Very clever guy called Rutherford came along, and he did an experiment. His experiment relied on a very, very thin piece of gold foil, which he fired a type of radiation called alpha radiation at. He did this in a vacuum, so the alpha radiation was able to move in a straight line through the bit of gold foil. Now, if we just look, we could look at maybe modelling that a little bit. If I go back and minimise my screen, extend the page a little bit, and go back to full screen. Oh. Full screen mode. Extend it back out. And I don't lose my extension, so we'll try to fit it in. What I can do is this. Unlock my little bit. Move it out of the way for now. Get rid of this. What I really want to do is show you the experiment or how it was done. So what he had is he actually had a piece of gold foil which was made up of atoms, and those atoms were all linked together. And those, well, the theory was it was supposed to be like a wall that actually went through and would block anything that was trying to pass through it. He fired these tiny particles of what he called alpha radiation at that wall, at that thin bit of gold foil. And he found what he was expecting to see is that they would be blocked by it. They would be stopped. So he would expect that when he fired them, they would hit this and they would bounce back. They would not be able to pass through the gold foil. But he didn't see that. His experiment actually showed that it did not bounce off of it In fact, the majority of these alpha particles passed through the gold foil. Okay? Most of them passed through. And every so often, one of them would hit something and would bounce back. Okay? And because of that, it would hit something and bounce back. He said there must be some part of it that is solid. There must be some part. So he suggested there was only a tiny little bit in the centre of an atom that was made up of something solid, and the rest of it was empty space. Okay, so that's how he actually refined the model of the atom. He suggested that it couldn't be a solid ball of positive charge with negative bits in it, because otherwise this alpha radiation would have hit it and bounced away. It must actually be mostly empty space with these centre bits in them that actually had something solid to them. And that was actually the discovery of the nucleus of the atom. So the centre of the atom is called the nucleus, and housed inside the nucleus, they didn't find this till later on, was protons and neutrons. Okay? He actually came up with this idea because most of the radiation, the alpha particles he fired at it, passed straight through. So most of it must have been empty space. And it was only the very centre, if it hit the centre, so a very small amount of particles, bounced off and came back. Okay, so that's how he actually discovered that the model, the plum pudding model, as we had it, this one here, was not correct because it would have hit that and bounced off. So he actually came with this idea of a nucleus right in the centre. The only bit that was solid was the actual centre, and the electrons were whizzing around the outside. Okay, so that's what he suggested, because most of it would just pass through. It's in fact so, the nucleus is actually so tiny that if you imagined a football stadium and you put like a tennis ball in the middle of the football stadium on the centre circle, the electrons would be outside the stadium, actually flying around. That's how much empty space there would be between the nucleus and where the electrons actually are. Okay? So that's why most of the radiation was passing through. So this nuclear model of the atom actually suggested the centre of the atom was an area of positive charge, just in the centre of the atom. And the electrons were whizzing around the outside and flying around, and they were in shells or orbitals, as we might call them. And it did get refined further, so we could see those shells and orbitals by Bohr. Okay, but that came a bit later, came a bit after Rutherford's experiment and how he designed it. So Thomson came up with this solid idea, the plum pudding model, a solid ball of positive charge, and with negative little electrons for it, and Rutherford refined it to be this nuclear model where it was, the centre was the nucleus, which was positively charged, and the electrons were around the outside. Okay? And the particles you find in the nucleus are the protons and neutrons, and they have a mass of 1 each. The electrons whizzing around, their mass is almost zero. They have very little mass, almost zero, you can say. It's actually, if you wanted to put down a mass for them, it is 1 over 1,860 is a number you can quote, but almost zero is fine for the mass of an electron. The charges of these particles, so we should remember it from chemistry, but the protons, I did it last time, are positively charged, the neutrons are neutral, and the electrons are the things with a negative charge. Okay, so that's the sort of development of the model of the atom and how it was actually changed throughout time. So that's looking at some models of the atom. We've actually covered the ideas as they've developed, so we've gone through that. We've done some good work there. We're now going to move on and look at nuclear fusion and nuclear fission. We're going to start with fission. Okay, this is again a topic that you may not have covered in class yet, so it may be new to some of you. So I'm going to go through the basics of it right now. It's by no means everything on it, but it certainly gives you a start into it. So, this diagram, this shows nuclear fission. The idea of nuclear fission is the breaking apart of a nucleus. That's what the fission bit is. Okay? And it's breaking apart of the nucleus of an atom. In most cases, in nuclear power stations, the fuel, the atom, the nucleus that gets broken apart is either uranium, 235, or plutonium. Those are the fuels that are used in a nuclear power station. So when we break that apart, it will split into two smaller nuclei, and the way it does that is it actually has a neutron fired into that nucleus. When it's fired into the nucleus, what actually happens is the mass increases. So when that neutron hits the nucleus, it absorbs it. And when it absorbs it, it grows and it becomes a bit heavier. Heavier by 1, because a neutron has a mass of 1. So it goes in, gets absorbed. That makes it become unstable. So when that nucleus has absorbed that neutron, it is unstable. It would be like me carrying a pile of books, and I use this example with my class. If I was carrying 20 books, I could do it. If I carried 30, okay, I could probably do it. 40, 50, 60, 100 books. If I was trying to carry 100 books, maybe I could just about carry them. If Miss Walker was to come and add one more book to the pile, that would make it unstable. I couldn't carry 101 books, that's the limit. And so I would end up dropping the books and the piles would split. Okay, that's what's happening. One more neutron gets added, the mass increases by 1, and the nucleus splits in half. When it does that, it releases or creates two new nuclei, and it also releases neutrons. In this case 3. It doesn't always have to be 3, but in this case, in this example, 3 neutrons are released. So when one neutron hits that nucleus, it splits in half and it releases 3 neutrons. And the great thing about it is, for us anyway, is that when this happens, this releases lots and lots of energy. So this releases lots of energy in the process of splitting. And we can harness that energy to make electrical energy, which we can use in our homes. So that splitting, that process of splitting, that nuclear fission, where the nucleus splits, releases energy, creates 2 new nuclei and releases 3 neutrons. Now some of you who've read about this might know what happens to these neutrons once they're released. They could go on and continue the process. They could become this neutron. Each one could hit 3 more uranium nuclei, and those in turn could split. If those 3 were to split, how many more neutrons would they release? They would release 9 new neutrons, and those 9 could go on and hit 9 more nuclei, and that could go on to release 27 more neutrons. And each time it gets bigger and bigger, and every time that happens it's releasing energy. So the amount of energy released grows and grows. This is called a chain reaction, because once it's started, it creates more and more of the same reaction. And if it's uncontrolled, that would become so volatile, release so much energy, that it actually could cause problems. It could lead to, if it was in a power station, a nuclear meltdown, or a problem such as that. Or in an uncontrolled nuclear explosion, it could lead to an explosion, an atomic bomb, if you like. That would be an uncontrolled chain reaction. So one neutron gets absorbed, the nucleus splits, releases 3 neutrons. That starts a chain reaction which could hit 3 more nuclei and go on and on and on. But the good thing is it releases energy. Bad things are, this also releases radiation, and this uses radioactive isotopes, which can cause harm to people, to objects around them. So if we absorb a certain amount of radiation, we can become damaged by it. So it's a downside to nuclear fission. It releases radiation, and that nuclear waste that it creates, that radioactive waste it creates, has to be disposed of. And at the moment, the only way we can dispose of it is put it in a big steel drum, filling it up with concrete, and then burying it somewhere, or burying it at sea. And that's not an ideal solution, but it's the one we've got. So what scientists are doing, scientists are actually looking at developing nuclear fusion. Now, whereas fission was breaking apart, fusion is joining together. That's what fusion means. So nuclear fusion is joining together the nucleuses, or nuclei I should say, of atoms. It starts with deuterium, and this is tritium over here. Both are they're actually versions of hydrogen. So hydrogen itself has 1 proton, and these are isotopes of hydrogen. How can we tell they're isotopes? They still have 1 proton. Both have 1 proton, so that means they're hydrogen. Anything with 1 proton is hydrogen. but they have a different number of neutrons. For those of you who watch my chemistry video will know an isotope is an element with the same number of protons, different number of neutrons. Okay? So these are both isotopes of hydrogen. Okay? Tritium, which you actually get from lithium, a reaction of lithium, which is very readily available, and deuterium, which you get from water, also readily available. So these are both readily available fuel sources. Readily available means there's lots of them. Okay, we can get loads and loads of these. So that's great about it. Okay, we can get lots of these things we use to supply energy. In fusion, what we do is we force them to come together. Now, when we're forcing them to come together, that actually takes energy. So this needs a lot of heat and or pressure as well. That is the sort of thing that is going on inside a sun. This process is happening inside a star, such as our sun now. So a star is carrying out nuclear fusion. If you've come across the term, it's a main sequence star where this is happening. Inside that star, such as our sun, is nuclear fusion. Now, it's because you need a large amount of energy to force these two positive particles close together. I said last time, opposites attract, likes repel. So if I've got one positive particle and another positive particle, and I force them to come together, that takes a lot of energy to do. So we need energy supplied in. We need a lot of heat or pressure as well to get these things to come together. But when they do, okay, they release a huge amount of energy in the process. And they actually convert, when they fuse together, into a helium atom, and they release a neutron as well. Now, the good thing about this is it still produces a massive amount of energy, but better than nuclear fission, the fuel is readily available. You don't need radioactive uranium or plutonium, and it doesn't release as much radiation as nuclear fission does. So you don't have that nuclear waste to dispose of. So this is a great process. The downside to it is scientists have been unable, to recreate the conditions needed for nuclear fusion. So it's a work in progress. Scientists are definitely working on it, and the reason they would like to do it is because if they could do it, they could get a near limitless supply of energy from very readily available fuels. So a great process, nuclear fusion, if we can actually get it to work. But unfortunately, in current terms, we haven't been able to. So it is something scientists are working on right at this moment. So that's the basics of nuclear fission and fusion. Now we've got two more topics to cover, and we're using up most of our time. So I'm going to fly straight into collisions, which is going to move us on. And before we think about collisions, what I want to talk about is, this is a distance time graph. Now there's lots of different lines on this. Okay, if you've got a really steep line, that is an object moving really, really quickly. So that's a really fast object. If you've got a shallower line, that's not moving as fast. But it is moving at a steady speed because it's a straight line. If the line is flat, the object is stationary. And when the line goes down, it could still be moving at a speed, but it's actually returning to where it came from because this is the start. This is zero distance. This curved line shows an object that's accelerating. So this object is not moving at its fastest speed, it's getting faster all the time. Only when the line becomes straight, if that line was to become straight after that point, similar to this line, would that be the fastest speed it was moving? Okay? Now when that line is straight, so we've got a nice straight line like this, we could find the speed that that object was moving in. The way we would do that is we would have to know the speed it was travelling at. So we've got lines along here. If these were, let's say, meters per second, so this was 1, 2, 3, 4, 5, 6, 7. Okay, that line goes up to 7 meters per second. And if this was time along the bottom, if these were seconds, that would be 1, 2, 3 seconds along the bottom. So that object has got up to 7 meters in distance in 3 seconds. So if we were to do that calculation, 7 would be the distance it would travelled, because I should start it, I'm sure you know this, but let's just put it up anyway. Speed is equal to the distance, which I'm going to run out of space and I'm right up top of the board, so it's not going to register it. divided by the time. Drawn that brilliantly up there, but hopefully you can see it. So speed is the distance divided by the time. So, as I said, my distance was 7 metres and my time was 3 seconds. So the maximum speed it would reach would be that sum there. Okay? So, when the line is straight, that's when it's moving at a steady speed. If the line's curving, it's accelerating. It will reach the maximum speed when the line becomes straight. Only when the line becomes straight will it reach its maximum speed. And I could work out what that maximum speed would be by doing the distance it travelled when the line was straight, not from the start. In this case it's from the start, but it would be the distance from when the line was straight divided by the time taken. Moving on, if we had an object such as this, so this would be a vehicle such as a minivan thing that was driving along and it collided with a car. If that was to hit a car, we could have before the collision and after the collision. Now this is a question about momentum. In all collisions, momentum must be conserved. So momentum must stay the same. So if I knew the total momentum of these two vehicles at the start, I could work out the total momentum of the vehicles at the end, after they've collided. Now, this vehicle is stationary, so the momentum it has is 0. Any object that's stationary has 0 momentum. But the conservation of momentum states, so conservation of momentum says momentum before must equal momentum afterwards. So that's called the conservation of momentum. Okay, so if I knew the momentum of this car is 0 at the start. The momentum of this vehicle I can work out. Its mass, 2,000, times velocity, 9. So 2,000 times 9 will tell me the momentum of that van. This has 0 momentum, so the total momentum is just the momentum of the van. After the objects collide, the momentum must be the same. So whatever the momentum of that van would be at the start, the momentum, the total momentum is the same. But the mass of the vehicles combined, if they stayed together, would be the masses added together. So the total mass of this would be 3,000 kilograms. That's the total mass of the vehicles. So using that and using the fact I've just worked out the momentum at the start, I could work out the velocity. Because momentum, and don't ask me why, but it's given the symbol P, is equal to the mass times the velocity. I would know the momentum, because I worked it out before by doing that mass times that velocity. I would know the new mass, so I'd know the momentum, I'd know the mass, I would have to work out the velocity. So I'd have to rearrange that. How do you rearrange a multiplication? How to get it to the other side? You would divide it. So it would be momentum divided by the mass. So the velocity would be equal to the momentum I worked out for this vehicle divided by the velocity. Okay. We're getting very close to time. There's lots more I wanted to talk about really, but just to wrap this up, hopefully it's been useful and you've picked up some tips. Give me any feedback that you've got and we will obviously put it towards our next video. We're planning on doing some whenever we can and hopefully you'll be able to use this in the mocks tomorrow. Remember, in this collision, if you're going to do it, wear a seatbelt because that increases the length of time it takes you to stop and therefore lessens the force you feel if you do have a collision. So seatbelts save lives, and that's not just a comment, that may be in the mock, so who knows. But it increases the length of time it takes you to stop, therefore lessens the force you're going to feel. Thanks for tuning in, and hopefully when we do another video we'll be able to have it live streamed and we'll look at ways we can answer your questions on the video. Thanks very much and good luck tomorrow.